Okay, I'm going to now start. Bismillahir Rahmanir Rahim. Okay, today we're going to do a specific latent heat physics chapter, chapter 22, as I posted in the group. So let's just get started. Okay, first, let's try to understand the title of the chapter, which is Specific Latent Heat. And this is sort of related to the previous physics chapter that we did, that was specific heat capacity. And I told you something about the term specific. What does a specific mean in physics? Can anybody answer? Does anybody remember? What does the term specific mean in physics? Yes, use the chat window to answer. Yes, good job, Hala. It means unit. Yeah, this is what I told you. Unit, any standard measurement. It could be unit length, depending upon what quantity you're trying to measure. So it could be unit volume, per length, per centimeters, and so on and so forth. So per some unit, okay? Per some unit, some standard unit, right? So that's what specific mean, okay? So we understand that. Then what does latent mean? What does latent mean? Yes, please use the chat window. What does the word latent mean? So once you understand the title of this chapter, it would be easier for you to understand what what we are trying to learn here. Yes, latent means hidden. Good job. And heat, what is heat? That's easy. What is heat? And what is the difference between heat and temperature? What is the difference between heat and temperature? And first of all, tell me, what is heat? Define heat. Does anybody remember? Good job, Hala. Good job. I like it. Flowing thermal energy. Good job. Yes. It is not just thermal energy, but thermal energy that flows from a hotter object to a colder object, because obviously the flow of heat is going to be from a hotter object to, from an object where there is more heat to an object where there is less heat, right? Just like in diffusion, just like, why? Because systems try to balance each other out. So when there are two systems in physical contact with each other and they have different amounts of heat, the heat tries to equilibrate by flowing from where it is more to where it is less, till both of them acquire the same level of heat. So when the two objects have the same temperature, the thermal energy stops flowing, right? Now, what is temperature? And what is temperature? Temperature is, okay, just wait a second. Okay, temperature is, yes, Aisha, good job. Yes, Saad, yes. Okay, how hot or cold an object is, yeah, that is also correct, but that is that's a very, yeah, that's a, like that's a definition of grade 2 3. So yeah, let's move on. Yeah, average kinetic energy, so Ajwa, Aisha, and Saad, you guys are correct. Average kinetic energy, yes, it is how hot or cold an object is, but scientifically. So I wanted a proper definition, but yes, the other answer is also correct. So specific latent heat. So now let's put together all the meanings and then try to understand. Specific per standard unit. In our case, this is per unit mass. Okay, this is per unit mass. This is hidden, and this is thermal energy that flows, right? So how can we define this? Putting these together, can we put them together? So come up with the definition of a specific latent heat without memorizing. Okay, we'll do the definitions when we'll do a melting and vaporization. Okay, now let's get to this. Recap of change of states of matter. I have done this many times with you as well as with other grades. This is just a quick recap, you know, change of a state of matter. You all know this, right? You all are familiarized with this. This is solid, this is liquid, this is gas, right? So as we move from solid to liquid to gas, these particles, they require energy. They require energy to do two jobs. One is to move faster, faster motion, more kinetic energy. What was kinetic energy? What was kinetic energy? Use the chat window. What is kinetic energy? It is the energy of dash. Come on, come on, come on. Yes, energy of motion. Yes, Hala, thank you. So faster means more kinetic energy. No, I think they want the camera to be this way. Can you see this straight? Can you see this straight? Okay, okay, good job. Okay, if you can see this straight, okay. So, okay, so as this energy is being provided, as we are providing energy, it is used to do two jobs. One is to increase their motion. One is to increase their motion, that is to increase their average kinetic energy, and average kinetic energy is temperature. So faster motion meaning more energy of motion. The other job that they're doing using the same energy is to move farther away from each other. As you can see, the distance here is greater than the distance here, and the distance in the gaseous state is even more, right? So you can see that as we are providing energy, not only are they moving more vigorously with more energy, that is kinetic energy, but also they are moving farther away. Why does potential energy increase when the distance between them increases? Can anybody answer that? Why does the potential energy increase when they go farther away from each other? Why does the potential energy increase when the distance between them increase? And I requested you guys to please use your real names. Now, I don't know who this physics is. And please do not share your videos. I plead you, I request you kindly, do not share your screens, because you see, when you share your screen, my screen is minimized, and that affects everybody, right? Who's trying to understand, who's trying to look at my screen. So please kindly do not do that. I expect that much consideration from you. Wait, let me check. Less attraction. You know what? Do it this way, and then, okay, less attraction between each particle. Potential energy is also elastic energy. Yes, Hala, you are close. Collision between particles decreases. Potential, I'm talking, okay, Amna, yes, you are right. That is gravitational potential energy, but I am talking about particles here, right? And we're talking about the changes of states of matter here. So explain me in terms of these particles. My question is that why does the potential energy increases as the distance between the particles increases? Yes, Hala is close. Hala is close. Hala said that potential energy is also elastic energy. Potential energy is also elastic energy. Yes, they do move far apart, physics, but why does the potential energy increase? That's the question. See, remember this? Remember this model? I have explained this to you before as well, that as I'm, like, for example, these two balls are two atoms or two particles, okay? Any two particles, right? Now, when I move them away from, yes, Amina, now you remember elastic potential energy, right? Elastic potential energy. So what is that? What is elastic potential energy? So consider that these are the two particles. They can be atoms or molecules, depending upon what substance you're talking about. And this elastic band is the force of attraction between them. Okay, it's the force of attraction between them. So now as I am providing energy, and I am moving these two particles away. Now what's happening, the tension, the elastic potential, or the tension in the elastic in this band is increasing, right? Now that tension you can think of as the elastic potential energy. It is actually elastic potential energy. Even in case of this band, it is elastic potential energy, right? So now what is this tension trying to do? Trying to bring them back together again, right? This tension is trying to bring them back together again. So when they are moving away, they're actually working against this potential energy. They're actually working against this potential energy. Now I can actually, feel the force of this band as I'm pulling the two atoms apart. I can feel the force in the band. That means there's some force which is trying to oppose what I'm trying to do, trying to oppose my hands, right? Now this is potential energy. This is potential energy. So I have to work against this. So this is what I mean by potential energy. So as they're moving away, as they're moving away, the potential energy between them is increasing because the force of attraction is trying to bring them back together. Okay? Now, in gaseous state, we all learned is gaseous state is attained when this band breaks. Gaseous, if I pull them too far apart, see, it broke, right? So a time comes when the elastic band breaks. At that point, at the breaking point, now move, zoom out, no, zoom out. Now when there is no elastic band between them and they are far away, this is gaseous state. This is how the gas molecules are. Now there is no force of attraction bringing them together. Again, now there is no force of attraction. Now they were without any force of attraction, right? So this is what happens when a substance changes from liquid to gas, right? So you have to appreciate this, because this will help us in understanding specific latent heat, right? Latent means hidden. Why is it hidden? Now we'll talk about it. So the increase in average kinetic energy increases the temperature. Temperature, we know, is the average kinetic energy. Change of state takes place due to increase in potential energy. Change of state, meaning from one to the other and to the third, right? So okay, let me talk about this a little bit more. So okay, so now when I increased the average kinetic energy, and when the substance was still a liquid, I was just increasing the tension, right? I was just increasing the tension, but they were also moving vigorously at the same time. So the kinetic energy, average kinetic energy was increasing. That means the temperature was increasing, right? And I can easily measure the temperature with the help of a thermometer. So with the help of a thermometer, we can easily measure the temperature. Now, but once there is change of phase, then only potential energy increases. The average kinetic energy stops increasing during the change of phase. During the change of phase, whether it is from solid to liquid or from liquid to gas. In both the changes of the states, the average kinetic energy during the phase change stops increasing, and all the energy goes into increasing the potential energy. And this door stops, and all the energy that we are providing is being used in increasing the potential energy only, which is helping the molecules to work against that elastic potential energy which is holding them together. They are busy breaking those bonds, or they are busy weakening those bonds. Now, another thing that I want you to appreciate is that when there is change from solid to liquid, the forces of attraction are only weakening, not breaking altogether. In the liquid state, there is some force of attraction is still existing. Okay, it's like in solid, they're this way, and in liquid, they have moved a little far away, but the band is still there. The force of attraction is still there. The distance has increased, yes, compared to solid, the distance has increased, But can you see the distance between them has increased, and yeah, the force of attraction has weakened, because the force of attraction decreases as the distance increases, right? Now, so from solid to liquid, the force of attraction is weakening, but from liquid to gas, it is totally breaking. Because in gases, there are no forces of attraction between gas molecules. No force of attraction, zero force of attraction. Zero force of attraction in gases, zero force of attraction. Okay, so what do you think needs more energy, weakening or totally breaking? Do you think that melting, that is from solid to liquid, would require more energy? Or do you think changing from solid to liquid, that is weakening the force of attraction, would take more energy, or total breaking would take more energy? Yes, total breaking will take more energy. That's common sense, because they have to completely get rid of that pull. See, when you are trying to break this elastic band, the most energy you have to apply at the end when it snaps, right? So yes. So therefore, boiling takes more energy compared to melting. Okay, appreciate that, understand that. Now, I have made this diagram. This is, maybe it might help you. Now, solid, liquid, gas. Again, the same arrangement, right? Now, I am showing that if I want to, in a substance's journey from solid to liquid to gas, we have to provide energy. We have to provide energy, right? Energy is required by the particles. And in the journey from backwards, from gas to liquid to solid, energy is released, meaning particles lose energy to the surroundings, right? Yes, exothermic, right? Now, I like to consider these melting points, melting points and freezing point, boiling point and condensation points as gateways. I like to think of them as gateways. It's easier for me to understand then. You know, they are like gateways. So in my journey from solid to liquid, like for example, this is one room. I like to think of it as this is one room, solid room. This is liquid room. This is gas room. And these are the doors between these rooms. So if a substance wants to get out from the solid room into the liquid room, it has to pass through this gate, this door. And if a substance wants to get back from the liquid to the solid, again, it has to pass through the same gateway, which in that case would be called freezing point. So basically, both these are the same thing. Both these are the same temperature. The only difference is, the only question is, are you going this way or are you going this way? Meaning, are you increasing the temperature or are you decreasing the temperature? Well, if you are increasing the temperature, then that means you are melting. Okay, and if you are decreasing the temperature, that means you are freezing. Same is the case here. Gateway is the same, point is the same. But what is the process? Process depends upon if you are increasing the temperature, in that case you are boiling, or you are if you are decreasing the temperature. In that case, the process is condensation. But the point is the same. Temperature is the same, but they are given different names depending upon which way you're going. So I hope this would help you. And remember, whatever increases the freezing point will also increase the melting point. Whatever decreases the melting point will also decrease the melting point. Do you understand? So that, because this is one gate, so they will move together. Either way, whatever you're doing. If you're decreasing the melting point, that means you're decreasing the freezing point. You are increasing the melting point, that means you're increasing the freezing point. Same is the case here. If you're increasing the boiling point, you're also increasing the condensation point. If you're decreasing the boiling point, you're also decreasing the condensation point. So understand that they go hand in hand, they go together. Right. So at these points, at these gateways, the average kinetic energy stops increasing. At these gateways, the average kinetic energy stops increasing, and it is only the potential energy that varies, okay, depending upon which way you're going, okay. If the distance between the molecules is increasing, that means you're increasing the potential energy. I told you, as the distance increases, potential energy increases. So, and as the distance is decreasing, if you're going this way, potential energy will decrease. But the average kinetic energy in both these gateways will stay constant, okay. I hope you understood these points. And okay, another thing I want to talk in detail about, what do I mean that a lot of potential energy is required when a substance changes from liquid to gas, that is boiling, right? Why is the boiling, why boiling takes more energy as compared to melting? So one point we already discussed, because they have to break the attractive forces completely. That's one thing, right? They have to completely break away. I should write completely here. They should completely break away from the attractive forces by the other fellow liquid molecules. You know, like, okay, for example, this is the liquid, right? These are water molecules, right? Now they have to break away. This molecule has to break away from the attractive pulls by the other molecules and has to get out. Now look at how much work this molecule has to do if it wants to get out. First of all, it has to completely break the attractive forces from the neighboring water molecules. That's one job. Oh, okay. Okay. Ishfaq? Ishfaq? Okay. I need to remove somebody from the, where's this participant thing? Who's this? Yeah, I think somebody has, intruded in my meeting. Okay. Yeah. Yeah, no, but I cannot get that. I cannot get that option. No, I cannot find him. I cannot find him.
What is he saying?
I will immediately remove any participant who tries to misbehave. No, he didn't leave. Okay. I will remove anybody with fake names. Anybody with fake names, I will remove immediately. I want actual names, okay? I want actual names. I had somebody intrude into my meeting and was sending me obnoxious messages. I don't want any fake names at all. I will have zero tolerance for that person. Okay, I am removing those people who are here with fake names. Let me remove first. Who else is here with fake names? Okay. No. Yes, yes. Was this is Fatma? No. Who is this? Yes. Yes. Okay. I removed. And those who are removed cannot rejoin. They cannot rejoin. Yeah. Yeah. Okay. Let's resume. Okay. No, the person the people who have been removed cannot rejoin. Play join and leave some, unmute themselves, chat with waiting room. Okay. Okay, I'm sorry about that interruption. Okay, so the first work that these molecules have to do is to break completely from these attractive forces by the neighboring molecules. The second job that they have to do, you can appreciate that they have to rise to the surface before they can evaporate. They have to rise to the surface. Okay, now in boiling, well, even no need to allow anybody. Okay, nobody will be allowed to enter the class anymore. That's it. Okay, so in boiling, the molecules will, I mean, even the molecules which are at the bottom can evaporate. I mean, that's why we have bubbles at the bottom of the containers, but they have to cruise their way up to the surface. Okay, they have to cruise their way up to the surface to some extent. Okay, and at the surface they have to cruise. Can you see that now? There are air molecules here, and now this water molecule, if it wants to go up, if it wants to rise up, it has to work. It has to cover some distance. It has to work its way out upwards. Okay, so in that process, it has to push the air molecules away and make its way upwards. Okay, the water molecule will move the air molecules away and make its way upwards. I will try to get some animated video on this. You know, there are a lot of good animated videos on the process of evaporation or the process of boiling. Okay, so this is the work that the elastic potential energy has to do. And what is that? Completely break away from the attractive forces by the other fellow liquid molecules, cruise their way up to the surface. Well, this is for evaporation, not for boiling. Okay, this is for evaporation, not for boiling. And then at the surface they cruise. Okay, ask Baba not to allow anybody to enter the class. That's it. Whoever is removed is removed. That's it. At the surface they cruise, push and make way for themselves through the air molecules. Okay, and then they rise up and away. Okay, so this is what the potential energy is used for. Okay, now all of this work requires tremendous amounts of potential energy. Tremendous amounts of potential energy. You have to appreciate that. Now that is why a steam burn gives you a scald as compared to hot water. Why? Because all of this energy that the molecules have acquired, I mean, they have used it to do this work, but they also possess it. So they are really high. I mean, those molecules which have the highest amount of energy, and by energy, I don't mean to say only kinetic energy, but total energy, meaning kinetic plus potential, or any other sort of energy that they might have. Okay, the total internal energy that the molecules have, all that total energy is too much. The molecules that have gone out of the liquid surface and have turned into gas, they are the most energetic. So when you get a steam burn, you have come into contact with the most energetic molecules, the most energetic molecules, and they have released all of that energy to your skin, and that has damaged your skin. And that's how we get steam scalds, right? And that is why steam is more damaging than hot water. Okay, steam is more damaging than hot water. Okay, so I hope you have understood that point. And then, so after understanding all of this, we can very well appreciate that stronger the forces of molecule, stronger the forces of attraction between the molecule, higher the latent heat, whether it is of melting or vaporization or boiling. Because higher the attractive forces, meaning more energy required to pull away, right, from each other, and therefore more energy required to change from solid to liquid and then from liquid to gas. So stronger the intramolecular forces, higher the specific heat capacity, higher the specific latent heat of fusion, and higher the specific latent heat of vaporization. Now, fusion is just another term for melting, and vaporization for boiling, right? In definitions. Now, the temperature during the phase change will stay constant. Why? Because the average kinetic energy is not changing, but the total energy is increasing because the potential energy is increasing. But remember, we cannot measure the average potential energy with the help of a thermometer. We cannot measure the increase in potential energy. And therefore, this change in energy is called latent heat, hidden. Hidden meaning we cannot measure it, okay? Because increase in potential energy cannot be measured, whereas increase in average kinetic energy can be easily measured with the help of a thermometer, because temperature is average kinetic energy. So molecules are gaining energy, we are providing energy, but the temperature is constant. That means all the energy is going to increase their potential energies. So the total energy is increasing, but we cannot measure it with the help of a thermometer. So we say that the temperature is constant, right? So the temperature will not change during the phase change, but it will resume increasing. It will resume its, once the phase change has been completed, meaning once all the ice has completely turned into water, all the ice has melted into water, then if you continue providing energy, then the temperature will start rising, right? So the rise in temperature would suggest that, okay, now the whole substance has melted and now the temperature has started rising again, because now the whole thing is water, okay? Now, let's try to define a specific latent heat of fusion without memorizing, okay? Don't memorize. Let's try to come up with this definition ourselves, right? Specific unit mass, okay? Latent without change in temperature. Heat is quantity of heat. Fusion means change from solid to liquid, right? Now let's arrange them in the form of a sentence so that we can define what this is, right? So we can say that the specific latent heat of fusion is defined as the quantity of heat. I'm trying to rearrange them in a sentence, okay? The quantity of heat that is required to change a unit mass from solid to liquid without change in temperature. Can I say that? Right? Can you come up with this definition on your own without memorizing? That specific latent heat of fusion is the amount of energy which is required to change a unit mass from solid to liquid without change in temperature. Why are we saying without change in temperature? Because we're talking about fusion, melting. So this is phase change, no change in temperature. That's why we say without change in temperature, because if there's change in temperature, that means that we are not talking about phase change. Phase change is not, I mean, phase change has not, I mean, we're not talking about phase change of a pure substance. Now I'll talk about the impurities and the effect of impurities and pressure on melting and freezing point in the next class, okay? So this is this, okay. Now let's talk about, Atika, latent means hidden. Latent means hidden. Amount of energy used for changing. Yes, good job, Amina. What does latent? Latent means hidden. Okay, when you get steam on your skin, it gives up its specific latent heat of vaporization to your skin as it changes from steam to water, and also gives up thermal energy as it cools down. So the total energy is more as the specific latent heat of vaporization of water is large, so that a steam burn is much more worse than a hot water burn. Is this right? Yes, it is right, but yeah, it is right. Yes, yes, you are correct. So basically, even if you don't mention this point of, that it cools down, even if you don't talk about the cooling down, the rest of the answer is still correct because it's a specific latent heat of vaporization itself is so much that it will cause burn. Okay. Okay. So now let's talk about the cooling curve of ethanamide. Okay, I'm sharing my screen. I'm basically showing you the same a picture, which is in your book on page 91. On page 91. Let me see. Okay, so now I will discuss this experiment with you a little bit. Okay, cooling curve. First of all, what is a cooling curve? Cooling curve. It is a graph of temperature against time. Usually, if we're observing a cooling of any substance, we take time, the unit of time is minutes, temperature is degrees Celsius, right? Now, let me first show you the cooling curve. Wait, let me, yeah. So temperature against time, right? Now, because we are talking about a cooling curve, meaning we're talking about decrease in temperature. So we will show decrease in temperature, overall decrease in temperature. Well, we can have heating curves as well, but in case of heating curves, you will show the temperature to be rising, right? So let's discuss this cooling curve. So as we are decreasing the temperature, we will plot down the decrease in temperature with each minute, or it depends, each 5 minutes. But the smaller the unit of time you use, the greater the precision, right? The precise your values are, or more accurate your values are. And where you see the graph flattening out, you know that there is, what's happening here? This is, what is this? Flat. Okay, label these parts with me. Label these parts with me. Yes, Ariba, good job. This flat portion is change of phase. Sorry, yeah, this is change of state of matter, change of phase. Right. Change of phase. Condensation, condensation. Okay, let's see if this is correct answer or not. Amna said condensation, Hala said freezing. Hala said freezing. Now, I told you, the name of the process will depend upon which direction are you going. So which direction are we going? We are decreasing the temperature. We are decreasing the temperature. Now, let's see. Can this be solid and then liquid? No. Liquid and then solid? Can this be liquid and then solid? So we are going this way, right? We are decreasing the temperature. We are decreasing the temperature. So either it could be from gas to liquid, or it could be from liquid to solid, either of these. So there is some change of state of matter going on, change of phase going on. Now, which one? That we will decide looking at the melting and looking at the temperatures, right? Now, you should have some rough idea about the substance you're talking about. Now, this is ethanamide. Okay, ethanamide is an non-polar substance. It is organic. Okay, and so its boiling point is its boiling point is around 80. Its melting point is around 80, and its boiling point is pretty high. So this graph is the maximum temperature. This graph is showing is 90 degrees Celsius. So we cannot have the boiling point here because the boiling point of ethanamide is 222 degrees Celsius. So that's pretty high. So that means we are between solid and liquid. We cannot be between liquid and gas because the maximum temperature this graph is showing is 90. So we must be between liquid and solid. Are you getting my point? This is boiling point and the melting point. So you should have some idea regarding the boiling point and melting point if you have to label it like this, okay? Melting point is around 80 degrees Celsius. So yeah, okay? So we are between, so what is this? This is, we are decreasing the temperature. We are decreasing the temperature. So if we are decreasing the temperature, when we are decreasing, the last state we get is solid. So this must be solid. Okay, if this is solid, this must be liquid. right? If this is liquid and this is solid, this must be melting. Ah, freezing. Yes, good job, Amina. This must be freezing. Why? Because we are decreasing the temperature. So I told you, the name of the gateway will change according to what we are doing. So we are decreasing the temperature, so we are freezing. If we had increased the temperature, then we would be melting. So yes, Amina, good job. So this, you should write freezing. Should write freezing, okay? Liquid, solid, okay? So this is your freezing point, which is the same as melting point. By the way, they can use the word melting point even for freezing point, so don't get confused, okay? Now, look at this graph. This is a heating curve. Okay, heating curve of ethanamide, heating curve of ethanamide. So as the temperature, so we are increasing the temperature. Okay, now let's label this diagram. What is this? Now this is also ethanamide and we are starting from 0. So this must be solid, right? And then after solid, what is the next phase change we come across is, yeah, now this time this will be melting because we are increasing the temperature. So this would be melting. Good job, everybody, good job. Ajwa, Saad, I'm happy to see your answers. Okay, now, again, now this is after solid, after melting, we get liquid. Yes, Shahid, Ariba, Hamza Salman, Huda, everybody, I'm happy. Okay, now after liquid, this is easy. Yes, this is boiling. We'll call this boiling. Okay, if we were going the reverse way, then this could have been condensation, right? Now, what is this? This is after boiling, we get gas, right? Yes, Hiba Siraj, yes. So, solid, melting, liquid, boiling, gas, okay? Now, after you have understood this, now let's talk about this practical cooling curve of ethanamide. Share screen. Share screen. Yes, okay. The cooling curve of ethanamide. Now, this is practical work. Now, the reason we study practical work is also to help us with ATP, right? Alternative to practical part of your exam. So we will ask whys for every step. For every step, we will try to ask ourselves why, okay? And let's see how many whys we can answer. Cooling curve of ethanamide. Fill a test tube with ethanamide, also called acetamide, and place it in a beaker of water. Now answer me, why half? Why can't full? Why shouldn't we fill it full? Why half? Yeah, and practically you have to talk about safety. You have to talk about safety as well. Yes, Amina, very good. Yes, I like it. Yes, because when you're heating, the liquid will expand and can also boil, right? And the beaker and the test tube is very small, so we should allow for some space. Okay, and why are we using beaker? Yes, very good. Yes, to give it a space if it melts. Good job. And yes, flammability. Yes, Hala, we should keep flammability in mind as well. Water bath is always to prevent any explosion or any flammability. Right, right. Good job. Yes, I like that. Now, move on. Then, why are we using a beaker of water to heat it? Why can't we heat it directly? Yes, same answers to avoid flammability, again, for safety purpose. Yeah, Abdullah. Okay. Okay. Wait, again, I have some intruder. I have some intruder.
I'm taking care of it. Yes, there is one. Yes.
Okay, thank you. Okay, so we don't want any flammability, okay? And we are using this beaker of water for uniform heating as well, for gentle heating. And remember, with water bath, you cannot go to very high temperatures, which are not required in a laboratory setup, right? Okay. Okay. Yes, yes, very good. The test tube might even break if you heat it directly. Okay, because of uneven distribution of heat, because the material the test tube is made up of is not a very good conductor, Um, therefore, it can cause cracking of the test tube, and so we need to heat the test tube uniformly, and that is only possible with the help of a water bath, right? And flammability, you talk about the, yes, okay. Now let's move on. Then heat the water until all the ethanamide has melted. So that shows us that that ethanamide probably is solid at room temperature. So it was solid, and we will keep it in the test tube, and we will heat it in the water bath till all of it has melted. And not only that it has melted, but its temperature should rise to about 90 degrees Celsius, right? And remember, I just told you the roundabout melting point of ethanamide was 80 degrees Celsius, and the boiling point was 222. So we are well below the boiling point, so no need to worry. Then remove the test tube and arrange it as in figure 22.1b. Now, why did we arrange this? Why did we arrange it this way? Why did we clamp it? What is the significance? Why can't we just keep it, in a glass, or why can't we just keep it in some holder, Oh, the chat is disabled in Zoom. Okay, I am sorry. The chat option has been disabled because of intruders. Okay, I'm sorry about that. So, we will have to give away the question answer thing. So I'm sorry about that. I won't be able to interact with you, especially in this class. Okay, we will try to fix this problem, and then inshallah. So, okay, so the advantage of using this setup as B is because we don't want the test tube to be in physical contact with anything else. Why? Because physical contact, yes, physical contact would cause loss of heat due to conduction, and that would affect our cooling curve. Then we would not get the right temperature readings in the thermometer. That will cause loss of heat due to conduction, and so our cooling curve will be wrong. We don't want that. So that is why we want minimum contact, as less contact as is possible. And furthermore, it is easier to read the thermometer and to keep the test tube in an upright position, okay, while keeping the visibility open, so that we can easily read the thermometer without any parallax error. And then the test tube is not in physical contact with any other thing, losing heat. Well, do you think this is 100% perfect experiment? Are there any errors in this, and what are the errors? We
should put a lid to prevent any radiation.
Evaporation, you mean?
Yeah.
Yeah. Okay. Yeah, we can cover it to prevent evaporation. But remember, we are trying to study cooling curve. So yeah. Okay. And then we can also. No, we're not trying to. Like, we have to keep it under normal conditions, like, normal conditions, the normal cooling curve. Okay, that is our purpose. Okay, now then, okay, record the temperature every minute until it has fallen to 70 degrees Celsius. Plot a cooling curve. Now, why 70 degrees Celsius? Because 70 degrees Celsius is 10 degrees Celsius below its melting point, which is 80 degrees Celsius. So we will get the liquid, and then the freezing, and then the solid phases in our graph. So that would be it. Now these are some of the reasons why we use a water bath. I found it somewhere, so I thought I would share with you. Thermal shock can cause the glass tube to shatter. Direct heat can burn or overheat the reagents, right? Because the chemicals we use in experiments are in small volume. So if we will heat it directly on the flame, it might burn the whole thing, the whole reagent altogether. So that will affect our experiment. The small volume can suddenly boil explosively, right? And then if we do have to heat in a direct flame, our container should be wide mouthed. Okay. Okay. Now, let's move on to, again. Okay. Now 1 kilogram. Now I have tried to come up with this. I'm trying to derive this formula. The heat required to melt a substance is the product of the mass and the specific latent heat of fusion. The heat required to melt a substance, whatever the mass is, you multiply that mass with the specific latent heat of fusion and you will get the total heat required to melt that substance. Now, how did we get to this? Now, a specific latent heat of fusion, yeah, due to fake entries, I had to disable the chat option. Okay, so that's why I cannot ask questions, and unfortunately you won't be able to answer my questions in this class at least. Okay, we'll try to fix this though. Okay, so the latent heat of fusion is the energy which is required to melt 1 kilogram. Remember? So like this is the ratio method I usually use. I don't know if you guys are aware of this. The specific latent heat of fusion, no, it's okay. Disable the chat. I don't want any more disturbance because it disturbs me and I cannot continue. You know, it affects my teaching. So a specific latent heat of fusion is the amount of energy which is required to melt 1 kilogram, right? Now, what is the amount of energy which is required to melt this mass? So what will I do? I will multiply the specific latent heat of fusion with the mass, and then that product, when gets multiplied by 1 kilogram, this is what you get. So this is how I derive this equation. So I hope you understand this. And there is law of conservation of energy behind this formula, which means that, no, not here in that other experiment. Okay. Now there's this experiment, how to calculate the specific latent heat of fusion of ice. Okay. That is on page 92, that practical work, this. I'm going to discuss this. Specific, show this, 92, specific latent heat of fusion for ice. This practical work. The waiting room notification is coming again and again, and your video is blocked. Can you please explain ratio thing again? Okay, then I won't be able to do this experiment then. Okay. See, how did I come up with this formula? How did I come up with this formula? I multiply, see, specific latent heat of fusion is the amount of energy which is required to melt 1 kilogram of mass, right? So if 1 kilogram of mass requires this much energy, then mass m kilogram will require how much energy? I will cross multiply specific latent heat of fusion with mass, and I divide it by 1 kilogram. So kilogram and kilogram get canceled. So what I'm left behind with is this, specific latent heat of fusion multiplied by mass. Okay, so the unit of this is joules per gram, or it can be joules per kilogram, right? Right. Okay, now let's move on to that experiment of a specific latent heat of fusion for ice. Okay. Yeah, okay, sorry. Okay, this is specific latent heat of fusion for ice. Now we have chosen a funnel because it's easier to carry crushed ice along with the electric heater. And what we will make use of this formula that we just discussed. Energy which is absorbed, energy which is required to melt the ice is the product of a specific latent heat of fusion into the mass of ice. Okay, and this energy will be supplied by the heater. So we are making use of the law of conservation of energy. That is, the energy can neither be destroyed nor created. And so the energy that is absorbed by the ice must be supplied from some source, and which in this case is the heater. Okay, and how do we calculate the heat supplied by any electrical device, such as an electric heater? How do we calculate it? Yes, Sundus, say it.
Using the power rating and
Yes, using the power. So if we multiply power by time, we
Yeah.
get the energy which is required to melt the ice. So for that, we need to know the power rating of the electric heater. If we do not know the power rating of the electric heater, then we have various formulae. We have various formulae that we can use, which include this. Power, if you know, these are the different formulae of power. BI, product of BI, I square R, V square over R. This we did in electric physics. Yes, power has two units, watts as well as joules per second. Okay, you can use any, and you know they are interchangeable. So numerically they're the same, but you have two different units. Okay, joules per second units are correct, and watts is also correct. Okay, so now, so using this, so heat supplied by the heater, we assume is equal to the heat absorbed by the ice. Right? Right. Do you think this is absolutely correct? This is 100% correct? That the heat absorbed by ice is equal to the heat supplied by heater? Do you think this is 100% correct? No. So then what are the practical errors in this? What are the practical difficulties in this? Some is wasted, very good. Some is lost to the surroundings, exactly. Saad, Hala, yes. Absorbed by the funnel as well, yes, good job. So then how can we correct it? How can we overcome these difficulties? What can we do? Yes, Tayyaba, yes, lost to the surroundings. Yes, we can insulate the funnel. Yes, that's a good idea. Or we can use a funnel which is an insulator, such as plastic, maybe. And yes, use a plastic funnel. Yes, that's a good idea. And yes, okay, shiny funnel, provided it's not a metal and it won't conduct away. Okay, other thing is that do you think that the ice is melting only by the heat provided by the heater? What if you just keep ice, I mean, if you just keep the ice funnel just like that in room for like 5 minutes? If, for example, the duration of your experiment is 5 minutes and you just keep the ice without the heater for 5 minutes in the room without the heater. Exactly. The room temperature, exactly. The room temperature will also melt. So how can we account for that? How can we account for that room temperature? So actually the heat absorbed by ice is the heat supplied by heater plus the heat absorbed from the surroundings. Actually, in practical, that is true. So now then what to do? So there are two ways to overcome this error. One way is to find out how much of the ice has melted due to the heat due to the heat from the surroundings. If we can find that out, we can subtract it from the total ice melted. And then the mass that we will be left behind with will be the ice that melted only purely due to the heat provided by the heater. But how can we get that? How can we get the mass of ice that melted due to the surrounding temperature? Good job, Amina. I'm really happy to see your answers. Yes, you're participating very well. Yes, we can set a control. We can have two funnels identical, but remember, the control has to be identical in all the other variables, exactly identical. Like the source of ice, the mass of ice, the type of funnel, the size of funnel, everything should be identical. Even the rate of dripping of water from the nozzle of the funnel should be identical for our results to be fair and accurate. Now, is that possible practically? No, there will be some differences. That is not practically possible. So an easier way that is given in your book is that what you do is use the same apparatus, right? And then, for example, if the duration of your experiment is 5 minutes, you keep that ice funnel for 5 minutes and then time yourself up with the help of a stopwatch. Let it melt for those 5 minutes without, and keep the electric heater as well, but don't turn it on. And keep the electric heater immersed in the ice, but don't turn it on yet, because whatever the temperature the electric heater itself has, before it got turned on, let all of that energy be transmitted to the ice, and let the ice melt due to the room temperature for 5 minutes. Measure that mass of water along with the beaker, and then you repeat. Okay, drain away that melted water after you have measured its mass, after you've weighed it. Then you turn the heater on again for 5 minutes, and then weigh the new mass of water. Okay, the difference between the two weighs will be the weight of water that melted only due to the electric heater. I hope you understood. If not, then replay the recording of this class. Okay, and then read the book, and then inshallah you will understand. Right, and then I'm also posting my classes on YouTube channel, so yeah, you can watch from there as well. We will find out how much ice melts into water during that time period by absorbing heat from the surrounding, for which we are doing the experiment. We will compensate for it by subtracting it from the mass of ice melted due to heater. So I hope you understood that. Okay, now once we know the amount of heat provided by the heater by multiplying its power by time, or and then the mass of water that you calculated. Okay, this is the formula, mass of ice melted by heater. Mass of ice melted by the heater plus surrounding, and minus the mass of ice melted by surrounding only. The difference would give you the mass of ice melted by the heater alone, right? And then you plug in the values and you can find out the specific latent heat of fusion. Now, these are some of the ways. Now the time is up. I'm about to wrap this up. How can we improve this experiment? By lagging the funnel that you have already talked about to avoid the heat loss to the surrounding. Another thing, electric heater should be completely immersed into the ice. Why? Now, the picture that is given in your book, you can see that more than half of the electric heaters is sticking out of the ice. So this is one way this experiment can be improved. Make sure the whole electric heater is immersed into the ice, because whatever heat is being radiated from this heater should be in contact with the ice. The ice should be able to absorb all of this heat, right? Otherwise, it would be lost to the surroundings by radiation, right? And we don't want that. So that's one way of improving the experiment. And another thing, ice should be finely shredded or crushed. Why? So as to increase the contact area between the ice and the electric heater. So as to increase the surface area between the ice and the electric heater, and so heat will be absorbed more efficiently, right? And then also make sure if your ice is too fine, it might drip from the funnel into the beaker. You don't want that happening. You don't want the ice to be dropping into the beaker. That will affect your results. So you can use a small, a net sort of thing. Yes, a filter paper, something like that, to prevent that from happening, right? So, okay, from here we will continue in the next class, okay? Yes, a gauze can also be used. Good job, Amina. Yeah, today's class was a little disturbed, and we will try to find who these intruders were. And Khuzaima, I have posted the links to my channel in the group. If you are in the group, please use those links. Okay, it's with my name. Okay. Okay, the intruders will be eliminated completely. Okay, and may not be allowed to enter my classes ever. Okay. Assalamu alaikum wa rahmatullahi wa barakatuh.